All right, here is one that looks really hard. It's got one of these blood test things, and we know those can tend to be difficult where they require trees, though in this case we can totally get away without using a tree. Or we can make one, it doesn't really matter. But as it turns out, A and B are actually going to be pretty easy, and C, well, I'll tell you, C is going to take some work. So let's take a look at this situation. We've got a lot going on. We read it, and there's sort of two different things that sound the same, but that are importantly distinct that can happen. And so I want us to label our events here, and I'm going to say H is the event where someone or a blood sample actually has HIV. So sample actually has HIV. And this is coming from, some sort of previous information, and they're telling you that we know it for sure, or we know that it doesn't for sure. And then let's say the event E is going to be this ELISA or ELISA, or however you want to say it, but this ELISA test is positive. And so that leaves us with some nice obvious complements. H complement would be that the sample actually does not have HIV, and E complement would be that the ELISA test is negative. So most of the time these two things will go together, positive and actually having it, as well as negative and not actually having it, but there's a little bit of error space, and so we got to be used to that. Okay, and so you have all the numbers given to you in the problem, and let's look at A. And it says when a new blood sample arrives in the lab, it'll be tested to determine whether HIV is present. Using the data from the training program, estimate the probability that the ELISA would be positive when it is applied to a sample that does not contain HIV. So what they are telling us here is it is being applied to a sample without it. So we are in this given H complement. So we are looking for the probability of a positive ELISA test, E, given H complement. And luckily we can just go into the problem, and it's saying based on the data here, and we can say, well, the ELISA test was positive for 37 of those blood samples, and there are 500 of them known to not contain HIV. ELISA was positive for 37 of those and negative for the other 463. And so this is going to be as easy as it sounds. It is going to be the probability that its ELISA test is positive and it's HIV negative. It does not actually have HIV. That's 37 out of 500, and we can do this out of 500 if we want. Divided by, it's going to be a little complicated, so let's actually just answer it as following. Let's just do 37 out of 500. We know that's what's going to happen here. I was trying to thread the needle there and point something out, but let's just look at it. We are in this world where it's the blood samples that we know do not contain HIV. There's 500 of them, 37 of them test positive. Okay. B, among the blood samples examined in the training program that provided positive ELISA results for HIV, what proportion actually contained HIV? So we're here asking for sort of this reverse, the probability of HIV given that the ELISA test was positive. The really nice thing here is that there are 500 samples of each, so there's nothing too complicated in this situation. It's just going to be the number that had both the HIV in the blood, and a positive test. That's going to be this 489 divided by the total number of positive tests, which is 526, which is coming from the 489 plus the 37. And so we get whatever decimal this is roughly equal to. Now, which I think I did at some point, this is equal to about, I better pause and do it. It's equal to about 0.924. Now, I can comprehend some of you looking around and being like, we usually use a table and these answers seem too easy. And really, this is all coming from the fact that there are 500 positive blood samples, like actually positive, not testing positive, literally known to have HIV, and 500 negative. It's that evenness, that balance that's making this so easy. But we can demonstrate this in a table if we really want to. So we can do H and H complement and E complement, and we're told a few of these things. One, we know that there's 500 both HIV and like having HIV and not having HIV samples. So we can do 500 here and 500 here. And we're told some of these other things. We're told that there are 489 of the 500 that actually are known to have HIV actually test positive. So it's 489, which makes this remaining number easily just 11. And then we're told that there are 37 and 463 in these places as well. And that's what gets us to this 526 and what ends up being 474, all adding up to 1,000 either along the columns or the rows. If we made a tree, you're going to notice all the same things are happening, where your first branch, I'm not going to do it because it would take too long, but your first branch would actually be 1/2 and 1/2. The probability of H is just the probability that, you pick a random sample, like a random single blood sample from this group of 1,000, and 500 of them, so 1/2 of them, are known to have HIV, and the other 1/2 are not. When these two values are different, we get all the weird stuff that we've been doing using Bayes' rule, but these are actually a little bit simpler. Okay, 7 minutes talking about the two easy ones. Going back, you would continue doing these two, but it's not necessary. We got our answers. So looking to see finally, when a blood sample yields a positive ELISA result, 2 more ELISAs are performed on the same blood sample. If at least one of the 2 additional, so we're talking 3 tests here because it's 2 additional ones beyond the first one, is positive, the blood sample is subjected to a more expensive and more accurate test to make a definite determination of whether HIV is present in the sample. Whew. Repeated ELISAs on the same sample are generally assumed to be independent, completely crucial here. Under the assumption of independence, what is the probability that a new blood sample that comes into the lab will be suggested to the more expensive test? So that means it's got to match like all the things they just described in here, if that sample does not contain HIV. So when we're doing part C, we got to think there are a few things that happen here. One, in order for it to get any additional testing at all, just the first 2 additional, it's got to be positive. And then, so it's got to be E. I'll keep my notation the same. It's got to be E on the first. Then, at least one of the 2 additional must also get a positive ELISA test. And note, this is all given H complement, given that the sample does not actually have HIV. What's the probability that we get, this positive test on the first, and then at least one of the 2 additional tests also getting a positive ELISA result? Now, there are 2 ways to do this, and I think they're both equally tough. One is, requires more work by hand, and then the other one is a little conceptually more difficult. So let's do the first one, sort of this constructive one, without using the complement. We're going to think there are 3 ways this could happen. Either you get an ELISA on the first, an ELISA positive on the first, and a positive on the second, and a positive on the third. Or you get a positive on the first, a negative on the second, and a positive on the third. Or you get a positive on the first, a positive on the second, and a negative on the third. So there's these 3 ways, and we're going to need to add up all 3 of these probabilities. Now, luckily, we have calculated, some of these numbers before. We've calculated the probability, and I'll even put this is all given H complement, all given H complement, all given H complement. Luckily, we've calculated this before. We know it's 37 out of 500, which is 0.074, the probability that any one ELISA test is positive, given that the blood sample itself does not contain HIV. So, the probability of getting a positive is 0.074 to the third, which is 0.000405. The probability of getting a positive, then a negative, then a positive is going to be 0.074. This is, again, given that the sample actually has HIV. Then the probability that it's negative, or sorry, that you get a negative test is going to be 0.926, and then 0.074 again, because you're getting a positive test on that third draw. And so we can throw that into a calculator. You get 0.00501. I'm going to do something similar here, so it's got to be positive, again, unlikely, but possible. Then positive again, 0.074. Oops. And then negative, which is way more likely if the sample does not actually have HIV. And that's also 0.005071. We add these three together, and we get 0.010547. Okay, so really unlikely. It's very unlikely if a sample is actually negative, to get this be sent off for this additional testing, but not impossible. It is a little bit more than 1% of the time. Now, I told you there was another way to do it. You could also think about it as the following. You need to get a positive test on first, which I will write as E, and then not negative on the two additional tests. Additional, it's my abbreviation for additional tests. And so what this is going to be is probability, and this is all given the sample does not actually have HIV. This is going to be 0.074. That's the probability of getting positive on the first one, multiplied by the complement of getting negative on each of the next two. 1 minus 0.926 squared. Close the parenthesis. And you should check me, but you'll get something that's slightly different because I had to do a little bit of rounding, but it is essentially all the same. 1 minus 0.926 squared. You can hear me typing it into the calculator, even though I'm also looking at a piece of paper that has this all done already. And we get 0.010546776. So it looks pretty much the same thing, a couple of tiny decimals in the end there. Okay, so that one took a long time. C is a tough problem, but it's not too crazy. And it's a long video. I appreciate you gutting through it and watching the whole thing.